All right, so this is the last section in chapter 5. Now, if you got confused by the previous section, this is an application of it, and hopefully it makes a little sense. A little bit more sense, rather. Not little, but a little more. So what I kind of tried to get at last section was this concept that the acceleration is the net force divided by the mass. But I want to modify this and instead say the acceleration of the system is the net force divided by the mass of the system. And the reason that I'm going to do this is because I have multiple objects now that are going to be acting. So I want to make sure that if those things are linked together, because they're an action-reaction pair, they're going to experience the same acceleration because they're all part of the system. So let's take a look at what that means. So when I think about something like a rope, we've already looked at that. We've looked at that concept of tension. Essentially, the tension is it's the force that's exerted on the box, okay? But therefore, there's also a box exerting the force of the tension, and those two are equal and opposite, and that's what causes the box to move. Now, that probably sounds really stupid, but essentially I'm saying that I'm pulling on the rope is pulling on the box, so the box moves. Now, most of the time in physics, we assume that the rope is massless, but there may or may not be a test question where we do not make that assumption. And because you guys are all so great at watching the videos, I'm going to give you a little hint right now, and that is if I have a mass tied here, and let's say that this is 100 Newton weight. We'll just say it's 100 Newtons. And the weight of my rope, let's say it's a really long rope, and the rope is not massless, but I'm going to say that the rope is tied off right here, and the weight of the rope is 50 Newtons. I don't remember exactly what the numbers are, but this I think this is right. Yeah. So my question is, what's the tension then in the rope? And the answer is kind of weird, but right here where it's tied off, at this point, the tension in the rope is 150 newtons. And that might not make sense because you're like, no, it's only holding 100 Newton mass. But at this point in the rope, it's also supporting the entire weight in the rope. It's hanging down from it, so it's 150 newtons. At this point in the rope, the tension is 100 newtons, and everywhere in between, it's somewhere between 100 and 150. So like right here in the middle, it's supporting half the rope, so it's 125 newtons. Anyway, that's a free test question for those of you who watch the videos. You're welcome. But it's just saying that normally in physics, we assume that the mass, normally in physics, we assume that a rope is massless, but I give you one test question where you got to think about that, what happens when it's not. Okay, so we got a quick check here, and this is starting to identify the concepts of these action-reaction pairs and how they relate to the acceleration. So here I have 3 50-kilogram blocks, but they're all at rest, and that makes sense because if they're the same mass over here, then they're going to have no net force. Now, as soon as one of these are in motion, it gets a little complicated, but yeah, it's going to stay in motion. So if I were to push this 50-kilogram box, it's going to move, and it's not going to stop moving because the object is in motion, okay? But anyway, right now, we're in static equilibrium, and therefore the net force is equal to 0. So in both of these cases, I should say in all 3 of these cases, we have identical free body diagrams where the tension is going to be equal and opposite to the weight, and therefore the tensions are all the same. Now, when the object is in motion or the masses aren't the same, that's going to change the tension because that will show how we'll get acceleration, and we'll take a look at an example problem like that this section. Okay, so pulleys. This should look really familiar because this is essentially our Atwood machine that we did our lab on. but we're going to continue to assume that we have massless strings, so we don't have to worry about those mass. And it's going over this massless, frictionless pulley. So when we look at that, there's no friction. This is known as an ideal pulley. And what that means is if B has some weight that it pulls down, let's say it's 50 newtons, then A has some force applied of 50 newtons. So it's how we just say that there's no friction being lost in this pulley, so that this is 50 newtons, but this is actually 48 newtons or something like that. So in a frictionless pulley, an ideal pulley, whatever weight we apply is what we should get the box to be, box A to also experience. That might have been a cause for error in your lab, but we'll assume that for our physics problems that they are perfect or ideal. So I got a quick check. The top of the block is accelerated across a frictionless table by the falling mass M. The string is massless and the pulley is both massless and frictionless. What's the tension in the string? So this is an application of Newton's third law, but there has to be an acceleration downwards, which means that there has to be a net force downwards, which means that the weight, mg, has to be greater than the tension force. And the reason that makes sense is because this, the mass, this force right here needs to outweigh the tension to give me the net force. So in this case, the tension has to be less than mass times gravity. Now, if it were going at a constant velocity, or if it were not moving, then the tension would be equal to mass times gravity. And if it were slowing down, like imagine, I don't know, like if you've seen The Matrix, where he's like, they're on the top of the building, and Neo like tries to grab the helicopter by a rope as it's like falling, then the tension would have to be greater because he's causing the helicopter to accelerate upwards as it's falling down. Okay, so we got an example problem, and this example problem is called lifting a stage set, and this is an application of ropes and pulleys. But it says a 200 kilogram set used in a play is stored in the loft above the stage. So if you've ever been to like a playhouse or like whatever you want to call it, they have multiple backdrops, and they change the backdrops by a pulley system. Now normally there's pulleys that create mechanical advantage, and we could talk about this, but it's not really something that's covered in our scope and sequence, but it is a physics thing where you have what's known as a block and tackle pulley or double pulleys. There's all types of different types of pulleys that we could get into a ton about, but they create mechanical advantage. But anyway, the rope holding the set passes over a pulley and then is tied backstage. So if I have a 200 kilogram set and there's only one pulley, there's no mechanical advantage, but the director tells a 100 kilogram stagehand to lower the set. When he unties the rope, the set falls and the unfortunate man is hoisted into the loft. What is the stagehand's acceleration? So let me see if I can draw a picture of this real quick. Here's the stagehand, and he's holding onto a string that's attached to a mass. We'll just call it a mass because I can't draw a full, backdrop. And we'll call that 200 kilograms, and he's only 100 kilograms. So if I were to take a look at these free body diagrams, this guy's got a weight going down, and this mass has a weight going down, and it's much larger than the man is. And the mass is tied to this string, which the only counteracting force of this string then is the guy's weight. Okay, so, but looking at the guy's weight, the counteracting mass is the counteracting force is the weight of the heavier object. So in this case, there is going to be a very large tension going up that is in fact larger than the weight of the man, but it's equal to the or it's caused by the weight of the set. So there's also this tension right here, and since this is an ideal pulley, and these two things are attached to each other, then these two tensions have to be the same. Okay, so let's go to the next slide where I have this drawn a little bit neater. Okay, so here is the a better picture, and we have a free body diagrams. Now again, I'm gonna say, and I talked about this in class a little bit, when we get into these types of weirder situations, which we won't spend a lot of time on, I'm gonna go ahead and say that this is the positive x direction. So now as I start to quantify stuff, I'll keep that in mind. So here's what I'm looking at. I want to find the acceleration of the man, which is going to be the same as the acceleration of the set. So here's how I set this up. I can say that the sum of the forces, I can call this, my picture has it as the y direction. I just said this is positive x. Let me just change that to positive y. So the sum of the forces in the y direction is equal to the net force in the y direction, which is equal to not the mass anymore, but the mass of the system times the acceleration of the system. So anytime I have interacting objects or multiple objects, that's how I'm going to call it. I'm going to call it the mass of the system times the acceleration of the system. So when I look at the forces, the sum of the forces, the force going in the positive y direction is going to be the weight of the set. So the weight of the set. And then that's going down, that's right here. Then I have the tension of the set is in the negative y direction. But then the tension on the man is in the positive y direction. And finally, the weight of the man is in the negative y direction. And these things are going to be equal to the mass of the system times the acceleration of the system. Not the set, but the system. So don't confuse that. SYS. Awesome. SYS. Kind of running out of room. So these two tensions, since they're part of an ideal pulley, they actually cancel out. And I get the mass of the system. I totally just screwed that up. Mass of the system times the acceleration of the system equals the weight of the set, which is the mass of the set times gravity, plus minus, struggling here, minus the weight of the man, which is the mass of the man times gravity. Okay, so now I have to solve for the acceleration of the system. So let me just clean this up real quick. All right, so to get the acceleration of the system by itself, it's going to be the mass of the set times gravity minus the mass of the man times gravity divided by the mass of the system, which is going to be the mass of the set plus the mass of the man. Okay, so like I said, the big concept is the sum of the forces equals the mass of the system times the acceleration of the system. And this kind of makes sense because the set is acting like a weight in free fall, but the man is acting like a counterweight. And the larger his mass, the less the acceleration. And it's not just about how close these masses are together, like a 2 kilogram and a 1 kilogram mass. It's about the total mass as well. So I'll talk more about that in class, and there is a test questions on that gets a little confusing, but I'm pretty sure I'll probably put it on the day before the test, and we'll talk about it. So the mass of the set is 200 kilograms times gravity, which is 10 meters per second squared, minus the mass of the man, which is 100 kilograms, again, times gravity, which is 10 meters per second squared, and then that whole thing over the two of them combined, which is 300 kilograms. So I have 2,000 minus 1,000 divided by 300, and I get an acceleration of the system of 3.33 meters per second squared. Okay, so the system accelerates at a steady or a constant 3.33 meters per second squared. And here it is again, probably a little bit nicer written out. But a quick little note: if the stagehand wasn't holding on, then this is actually a lot easier. There is no countermass, so there is no tension, and then the only force is the weight. Well, that's just an object in free fall. So essentially what's happening is the man is acting as a counterweight, and the heavier that man, the slower the acceleration of the system. And that's actually going to do it as an introduction to this. And like I said, it's an application of Newton's third law, and then it ties into the other Newton's second law and Newton's first law. So it can get a little confusing. Luckily, like I said, this is not a heavy hitting point. It's just getting into some of the applications, which when you get into physics, like my goal is to give you and show you some of the applications, not necessarily to make sure that you understand and can execute them all, but to understand why or what they can be used to do. But that wraps up chapter 5. So we're going to do a lab, and then we're going to go tie in chapter 6, which is all about an application of forces and looking at going in uniform circular motion and taking a look at what's known as the centrifugal force, and some of the really cool applications of that. And we'll do that in the next segment.